All right, greetings everyone. Welcome to our third video now for section 3.3. We're going to continue on with some more differentiation rules. And we've talked about so far finding derivatives of specific types of functions. Now we're going to expand that a little bit more and look at rules that work for when we have functions kind of related to each other, or really being multiplied or divided by one another. So it doesn't matter what the functions are. What do we do when they're being multiplied or divided? Okay. So as an example of that, let's look at this function here. So we have the function f of x equals x times e to the x, and we want to know how to find the derivative. Well, we do know how to find the derivative of each of the functions we see here individually. So if I broke this apart into the function x and e to the x, well, we've already learned how to take the derivative of those each, right? So d dx of x, derivative there would just be 1 using our power rule. And d dx of e to the x, as we learned, is just e to the x. So that might make you think then that the derivative here, f prime of x, should be 1 times e to the x, right? Right? If only it were that simple. Okay, so what are we going to do for this? Well, let's kind of look at trying to develop a formula here. So let's say we have two functions that are both differentiable. And remember, that means that if they're both differentiable, we can take the derivatives of them. So we have the function f and the function g. We want to find the derivative of f times g, okay, which is what we just saw before. So in the last one, like the function x would be our f, the function e to the x would be our g. So how would we find the derivative here? Well, we're going to use the limit definition of the derivative to come up with this formula. And I want to say, as we're doing this, this is not something I'll ask you to do on a test or a quiz, but I think it's very useful for us to get used to kind of the development of formulas and where they come from, okay? So let's use the limit definition here. And as we do this, keep in mind that our function here, even though it's the product of two functions, the function we're looking at is f of x times g of x. So if we can use our limit definition, well, we know that the limit definition says we take the limit as h approaches 0. We evaluate our function at x plus h. So we plug that in everywhere we see x, which we can do that for both of these by plugging them into the x's there. So we'll have f of x plus h times g of x plus h. And of course, I didn't leave myself enough room. Let me go ahead and rewrite this. Okay, so we'll write it as a limit as h goes to 0 of f of x plus h times g of x plus h minus, and then we just do the function evaluated at x. So in this case, that'd be f of x times g of x all over h. Okay, so again, we're just setting things up using the limit definition. And then I'm going to add something to the top. I'm just going to write it down, and let's see if I've really changed much by including this thing that I'm including. So what I'm going to do is I'm in the middle here going to subtract f of x plus h times g of x and add f of x plus h times g of x. And at the end there, we should still have that minus f of x times g of x, and I apologize, I ran out of room again. Okay, so this last part I'm writing, this is on the top. And let's first of all think about why that's legal. Well, notice in the middle there, I've got a minus f of x plus h g of x and a plus f of x plus h g of 8x, and there should be a g in there. And notice that if you combine those two things, they really make 0, right? So putting those two into the fraction there, I've just made 0. Okay, and then I want to look at each of the pieces, or divide the top into two pieces. So I have this first piece, the f of x plus h times g of x plus h minus f of x plus h times g of x. And then the second piece is this plus f of x plus h times g of x minus f of x times g of x. And notice in each case, they have stuff we can factor out, right? In the first two terms, we see that they have f of x plus h in common. In the second two terms, we see that they have g of x in common, right? So let's look at what happens if we factor those out. What happens to our limit? I'm going to go ahead and rewrite this again. So if I factor those out, what we have now is something that looks like this. So I will have f of x plus h times g of x plus h minus g of x minus, plus g of x times f of x plus h minus f of x. Okay, and this is all still over h. All right, cool. Now notice, on the top, we have two things being added together over a common denominator. And we've done this little trick I'm about to use here several times already, where because the things on the top are being added, we can actually break this into two fractions. So what this will look like now, just rewrite it all. So we'll have our limit here still, and try to write that small. And then we're going to have f of x plus h times g of x plus h minus g of x, and just that over h, plus, in the second part, we'll have g of x times f of x plus h minus f of x all over h. So we've kind of gone and separated this into two fractions. And notice that we're taking the limit of these two fractions being added together. And if you remember from our limit rules, that allows us to break this into two pieces. So we can make just a limit here and take just a limit here. So let's look at the limit of the first part. So if you look at just the limit, as h approaches 0 of f of x plus h times g of x plus h minus g of x all over h. And first of all, notice the stuff that's on the top, or actually this fraction we have here, of this f of x plus h times that stuff. Well, another way you can write that is the limit as h approaches 0 of just f of x plus h times the other stuff, the g of x plus h minus g of x all over h. Okay, and that's because when you multiply the f of x plus h times that, you can make it over 1, and it would give you back this thing that you've got here. And the reason I point that out is now we have a limit of two things being multiplied. And if you again remember our limit rules, that means we can break those into two separate limits. So what this becomes then is the limit as h goes to 0 of f of x plus h times the limit as h goes to 0 of g of x plus h minus g of x all over h. Okay, and let's look at what happens in each of these limits. So for the limit as h goes to 0 of f of x plus h, well, as h goes to 0, this part on the inside here, the x plus h, is going to get closer and closer to just x. So this limit will just be f of x. And what about this second limit? Does that look kind of familiar? Yeah, I think you guys are right. That would give us the derivative of g, so g prime of x, right? And so that's what the first fraction ends up giving us. If we go through and do with the second fraction, the one that had the g of x times f of x plus h minus f of x over h, you can imagine we get a similar thing. And then if we put it all together, what we see is that the derivative of this function here, based on the limit definition, is going to be f of x times g prime of x plus g of x times f prime of x. And so that, y'all, is how we'll take the derivative of the product of two functions. Isn't that fun? Yeah, I thought you'd think that. Okay, so here's our moral of our story. Two different ways to kind of think about writing the derivative based on the product of two functions, but these are really the same thing. So firstly, if we're using this ddx notation, so we have the derivative of two functions being multiplied. Okay, and again, we have to be able to break it into two functions being multiplied. We can do the first function times the derivative of the second, plus the second function times the derivative of the first. Okay, and the second part down here, it says the same thing, it just uses that prime notation. So if we're trying to find the derivative of f times g, that's f times g prime plus g times f prime. Okay, so let's use that now to find the derivative here. And in this case, since I already used f to name that function, the main function, I'm going to call this one here h, and this one here g. So then f prime, based on our derivative product rule there, would be h of x times g prime of x plus g of x times h prime of x. Okay, so let's do that. So h of x, that function is just x times, well, the derivative of the function g there, we saw the derivative of e to the x is just e to the x, plus now our second function, so the g of x, so e to the x, times the derivative of the first, and the derivative of x, as we mentioned earlier using our power rule, is just 1. And if we simplify this, we get x times e to the x plus e to the x, and that'll be our derivative. Okay? Fun stuff, right? All right, so that's what we do when we have two functions being multiplied. So what would be the next natural thing we might want to know? Right, what do we do if we have two functions being divided? We're not going to go through the proof of that one. I'll just show you the rule. Before we do that, though, here's some practice that you guys will see in a classwork assignment, so I'm going to skip over that for now. Although, I do want to point out one thing here. When you are looking at using the product, remember you have to look for your two functions being multiplied. And if you look at this second one here, notice the first function is e to the t, but the second function is this whole thing here. So 2t plus cube root of t. So e to the t would be like your f of x, or f of t in this case. This 2t plus cube root of t, that would be like your g of t. Okay? All right, now let's look at what we do when we're trying to find the derivative of two functions being multiplied. So you see there in that ddx notation, so if we have f of x divided by g of x, the derivative will be g of x times the derivative of f minus f of x times the derivative of g all over the original function g squared. Whew, that's quite a bit, right? Okay, using the prime notation, if you have f divided by g, it's be g times f prime minus f times g prime, and again, all over g squared, and I'll just keep emphasizing the function on the bottom, you're just using the original function g and squaring it. You are not taking the derivative there, okay? Now, I know this one looks like a lot to remember, and it kind of is until you use it a lot. So one little kind of, if you call it like a rhyme or way to remember it that students have used is, so if we think of like each of these functions, f and g being the high one and the low one, and then like if you think like d representing derivative, one way people remember this is low d high minus high d low, square the bottom, and there you go. So I'll say that again, low d high minus high d low, square the bottom, and there you go. So that's one way to remember it if you need help. Okay? So let's use the quotient rule now on this function. So our function is f of x, and so we've got a high function and a low function. So I'm again, even though I already used f, I'm going to call this top one h of x, this bottom one g of x, and that top one would be like our high, the bottom one would be like our low. So if we're using our quotient rule to find f prime, we do low functions, so x to the 7th, times the derivative of the top, and just some scratch work here. If we're doing dx of x squared plus 1, remember we can do the derivative of each parts of that function separately. So we can do the derivative of x squared, which will just give us 2x. And the derivative of 1, do y'all remember what the derivative of a constant like that is? Right, it's 0. So we just get 2x for our derivative here. So we'll have x to the 7th times 2x minus, now we do the high function, which is x squared plus 1 times the derivative of the low one. So x to the 7th, using the power rule, we get 7x to the 6th, all over, and then remember we square the bottom, but it's the original function. So x to the 7th squared. Okay, so again, it's our low d high minus our high d low. We squared the bottom, and now here we go. And we can just do a little cleanup here. So I can write this as, well, if I do 2x times x to the 7th, that gives us 2x to the 8th. And you can do minus 7x to the 6th times x squared plus 1 all over x to the 7th squared. Multiply the exponents there, you get x to the 14th. Okay. And in this case, if you want to, you can actually just leave your answer just like that. I'm not going to want us to simplify anymore. If you wanted to, you could distribute this negative 7x to the 6th into both of these. You might be able to reduce some stuff because of the x to the 14th on the bottom. But for the most part, I'm not too concerned about that. We can just leave it just like this. Okay? All right, that's all I've got for now. Thanks for watching.